All nucleophilic substitution reactions require a good leaving group. If there is not a good leaving group present in the molecule, there's nothing to leave. And whether it's going by the SN1 mechanism or the SN2 mechanism, in both of these cases, there has to be a leaving group available to leave. If there isn't, you can't get into the game at all by either mechanism. So what's the rule for a good leaving group? Well, any atom or group of atoms, we call it X, is a good leaving group if it is a weak base after accepting both electrons from heterolytic cleavage of the CX bond. Okay, so weak base. This brings us back into the concept of Bronsted acid-base reactions that we saw in the first part of Unit 3. So we need to go back and look at our good old friend, the pKa table, and what I've done is extracted certain examples from a pKa table. So for the purposes of this course, a weak base is one whose conjugate acid has a pKa of approximately 0 or less. You might see that I have 0.18 at the bottom of this list, but 0.18, if we round it to the nearest whole number, is 0. Okay, so what are some good leaving groups? I minus, Br minus, Cl minus. So what you have to do is look at the pKa of the conjugate acid. So first of all, the conjugate acids of these three are Hi, HBr, and HCl. And if you go to the pKa table and look them up, you get pKa's of -10, -9, and -7 respectively. Okay, hydrogen halides are, at least these three are strong acids. You notice that F minus is missing from the group. And you'll see that on a different table on the next slide of things that are not good leaving groups, because HF is actually a much weaker acid than HCl, HBr, or HI. Okay, next on the order of pKa's are a couple of beasts that you may not recognize. They are sulfonate anions. They are not exactly sulfuric acid or the conjugate base of sulfuric acid, but they have similar structures in that they have two of the SO double bonds. So the first one is called a methane sulfonate, which is sometimes shortened to be mesylate, and the second is a paratoluene sulfonate, which is sometimes shortened to be sulfonate. The conjugate acid for the first one is methane sulfonic acid. The conjugate acid of the second one is paratoluene sulfonic acid, and both of these acids are strong acids and have pKa's of -6.5. Finally, water is a good leaving group. Its conjugate acid is H3O+, which has a pKa of -1.74. And to round out the list, the trifluoroacetate anion, CF3COO-, which is the conjugate base of trifluoroacetic acid, that has a pKa of 0.18. Remember this, the inductive effects of those three fluorines make the trifluoroacetate a weaker base than plain old acetate, which is not really a good leaving group. Okay, so now that we've talked about what is a good leaving group, I need to give you some examples of things that organic chemistry students commonly try to make leaving groups, especially under the pressure of an exam situation, that are not good leaving groups. Okay, so don't make the mistake of trying to use anything from this list as a leaving group. Okay, specifically F minus, OH minus, H minus, or CH3 minus. The conjugate acids of these, HF, H2O, H2, and CH4, have pKa's of 3.2, 15.7, 35, and 50, respectively. You may be tempted to try to make hydrogens leave, because hydrogens leave in acid-base reactions, but in acid-base reactions, they are leaving as H+. Remember, a leaving group, by the definitions of this lesson, is something that has to accept the electrons after heterolytic cleavage of a CX bond, and CH bonds are never going to cleave to put the electrons in the hydrogen, because hydrogen is less electronegative than carbon is. But even if you did, you would be making a really, really strong base of hydride, whose conjugate acid pKa is 35. Okay, so to recap, every nucleophilic substitution reaction needs a good leaving group, and in the course of this lesson, we went over what makes something a good leaving group and some examples of some good leaving groups.